Good evening, ladies and gentlemen. Thank you for coming to the second event for the year 2017-2018 from the West Midlands region. And we are really sorry for the last change of plans on the schedule for today. But thank you, Stuart, for jumping in with the subject. So today's is natural ventilation in schools and commercial buildings. And while we all know that the Baby 101 publication for schools is imminent for quite some time now, we are all interested in that subject. So we have Passivent today, Stuart Rimell for Passivent, to discuss more on that subject. And can you please also fill in the feedback forms at the end of the event? Thank you very much. Also, the schedules for this year is on the table for whoever doesn't have that. Thank you, Stuart.
Good evening, everyone. My name is Stuart and I'm from Passivent. And I'm here to talk about natural ventilation in schools and commercial buildings. A little bit about Passivent. So Passivent is part of a group called BPD, which is Building Product Design. We also have businesses called Protect, which is to do with membranes for timber frames and roofs. Kingfisher, which is architectural louvers, and Glidewell, which deals with ventilation in domestic properties. We are then part of the BPD holdings, which have other businesses as well. We are fully accredited to 9001, 14001, 18001, which is independently tested. And now the natural ventilation. Obviously, the principles of natural ventilation are not a new thing. They date back many, many years. There's evidence in ancient buildings of use of natural ventilation using wind-driven to remove air from buildings, and also thermal massive buildings to keep buildings cool in hot climates. So, in England, development of forced ventilation using natural wind came about in the 18th and 19th century. This was mainly due to the theory of the miasma theory, which was that disease was spread by dirty, stagnant air, and therefore they wanted to get air removed from buildings so that they didn't do this anymore. You can obviously see a couple of buildings there. You've got the Natural History Museum at the top and the Houses of Parliament at the bottom, which both use these principles. The NatVent project was something that was done in the 90s, which Passivent was part of, along with some other European companies and associations. It was designed to overcome the perceived problems with natural ventilation in the commercial industry. They were trying to design practical uses for natural ventilation in commercial building, and the study identified many benefits of natural ventilation. So you had environmental gains, so you had a reduction in CO2 emissions, obviously without having to use electricity and to run air conditioning units and fans, you reduce the CO2 emissions, and also includes the use of ozone-depleting substances such as refrigerants. Also productivity gains. 90% of occupants surveyed preferred natural ventilated buildings to air-conditioned and other mechanical ventilated buildings, and you had fewer incidents of sick building syndrome, which is caused when you have dirty, stagnant, not dirty, but air in the building not being changed, so you get build-up of CO2 levels, which can cause headaches, nausea. There's instances of people who've been in a room for 2 hours or so having a meeting that have to go out of the room to be sick because of usually because of high CO2 levels. Also showed some cost benefits, so it had lower capital costs and also much lower maintenance costs, obviously without having to worry about fans and parts for fans and moving parts. There was much less maintenance costs. Obviously had a reduction in space required for plant area, and also obviously a massive reduction in energy consumed by equivalent building using air conditioning. Moving on to climate change. So 37% of CO2 emissions in the UK derive from energy consumption in buildings, and heating and cooling can account for half of this in each building. So therefore, well-controlled and energy-efficient ventilation is a must to reduce the emissions. Obviously, the government brought the Climate Change Act in 2008, and the key thing of this act was to reduce the 1990 CO2 levels by 80% by 2050. So you had renewable targets and specific authorities, so places such as Norfolk, obviously with the wind, putting in lots of renewable energy, and other areas in the UK as well. Obviously, approved document L was targeting carbon neutral buildings by 2019. The minimum BREEAM are very good for schools. So, in 2015, the UK emissions were 38% below the 1990 levels, which meant the first carbon budget had been met, and we are on track to meet the second and third. Currently, we're not on track to meet the fourth, which is the 23-27 period. They're showing that it's not quite going to make it. In order to meet the 2050 levels, from now on we're going to have to reduce our CO2 emissions, our carbon emissions by 3% a year to try and meet the 2050 target. So regulations and guidelines. So regulations are designed to reduce CO2 emissions in our buildings and provide a healthier indoor environment for everyone, obviously for school children in schools and obviously for workers in office buildings. Some documents that we need to overview in terms of ventilation, we always look at is document F, which is obviously for ventilation, document L, which is energy, and BB 101, which is obviously ventilation in schools, and BB 93, which is to do with acoustics in schools. Obviously the Scottish one is for Scott. So approved document F. So this is for guidance for indoor air quality, so it means ventilation. It refers people to obviously the Cibse guide AM10, which is for the natural ventilation of commercial buildings. General offices are recommended to be ventilated 10 metres per second per person, and obviously for schools it refers people to BB 101. Part L obviously is aimed at reducing energy consumption to reduce the CO2 emissions. It recommends that solar gains are reduced to low obviously internal summer temperatures, therefore less air conditioning is required in the summertime. Obviously if you've got a building with a big glazing facing south, then you know that during the summer that's going to get very hot, so it's obviously to try and design your building so it's not going to get overly hot in the summertime. And obviously again directs people to BB 101 for the internal heating for schools. Skip over to Scotland. So the importance of ventilation. Obviously is need to maintain the CO2 levels to a minimum, obviously inside to reduce the likeliness of sick building syndrome, and also increase the performance of the occupants. Obviously if people are breathing in stale CO2 laden air, they're not going to be performing as well as they can. And obviously also to make sure the internal temperatures are regulated to prevent overheating, especially in the summer periods. So BB 101, obviously currently in revision, going to be launched any day. We can't seem to get an actual day out of them as to when it's going to come into effect. Obviously the existing BB 101 is just titled Guidelines on Ventilation in Schools. With the new one, you can see they've added in thermal comfort and indoor air quality, so there's obviously a lot more concentration on that element of the builds, not just the actual ventilation. So some parts of it. So it refers to the environmental circle. Now, the environmental circle is the same. So the outside circle, these are all the areas you need to look at. And the way it's set out is to say, well, okay, if we look at the air velocity, if we increase the air velocity, that's going to increase the background noise. So we need to make sure we don't increase it too much to create too much background noise. And of course, again, if you're going from the background noise, if you want it at a low level, so it's a library, okay, how is that affecting the air velocity? What do we need to keep the air velocity down to make sure that we keep it in quiet space? So here it's showing what effect doing one thing potentially has on another thing, and obviously you've got to try and balance it all. And then figure 1.2 refers to the types of ventilation systems you can use. So obviously it's a sliding scale. So you've got With fully natural ventilation at one end, which is essentially based on opening windows, and then to your full mechanical system, and then all your different areas in between. So we go some sort of just opening windows to sort of window actuators controlled by a control system, to actuated louvers, roof terminals, and then through to hybrid systems where you've got your recirculation to try and keep heat within the building, and then through to your full mechanical. Obviously, depending on the situation of where the building is, depends on what sort of system you might choose. So sections 2 and 3 cover workplace health and safety. So sort of saying that you need to look at the welfare of the occupants, making sure that you keep their health as a key factor. With this, the guidelines with natural ventilation and hybrid systems, you have a maximum daily average of 1,500 parts per million, this is CO2, for 20 consecutive minutes, as an average, and then no more than 2,000 parts per million for 20 consecutive minutes each day. If you go for a full mechanical system, these are reduced to 1,000 and 1,500. So with a natural or hybrid system, you get a bit more leeway on your parts per million ratings. So it looks at thermal comfort, so obviously going through an ISO 7730 for comfort standards. So, and also EN 15251 to prevent summertime overheating. It also looks at Cibse's TM52 for doing the thermal modelling, to obviously make sure it passes and it's not going to create an overly hot building. The other thing to look at is the prevention of cold drafts. Obviously you don't want people with cold drafts on them, otherwise that's going to affect them just as much as overheating. And looking at positioning of inlets and outlets. Obviously if you've got a school next to a busy road, you don't want to be positioning inlets next to that road. Obviously you can bring in other emissions. And also if you've got other parts of the building, for instance kitchen extract or toilet extract, you don't want to position any of your inlets anywhere near those areas. So computational modelling. So we use several different things, but the main one we use is the bulk airflow calculations at initial stage. This will be able to allow us to calculate how much air is required to get in and out of the building. Using those calculations, we can then work out areas for actuated louvers or air turrets, and then moving on from that, once you've got those airflow calculations, you can then put it into a dynamic thermal model to assess the building to make sure that you're going to pass all the thermal model criteria. Design. So a good net ventilation strategy is one that delivers cost-effective, energy-efficient ventilation whilst ensuring the legislative requirements are met. Fully natural ventilation, so these are several different stages you can go to. Go fully natural, enhanced hybrid ventilation, and natural vent and mechanical recirculation. So a hybrid. I'm going to get some of those now. So obviously, your most basic is a single-sided strategy. Where you've got inlets at the bottom, outlets at the top, so your cool air will come in, your hot air will rise and then pass out. Restrictions on this is the fact that your effective allowable depth on the room is 2.5 times your floor to ceiling height. So if you've got a 3 metre high ceiling, for instance, you can only go 7.5 metres deep, or 7.25 metres deep in that room. Done my calculations from there, 6.25 metres. Anyway, 7.5 is right. Sorry, brain freeze. So yeah, so that's the simplest solution. Obviously, we move on to a crossflow strategy. This is where you have inlets and outlets on opposite sides of the building. The advantage of this is obviously it doubles your effective depth of the room, and also it works in both directions. So if your wind is blowing that way, it works that way. If your wind's blowing this way, it works that way. With the single-sided, obviously, if your wind's in the one direction, it works really well. If your wind's in the other direction, it has a detrimental effect on the performance. We move on from crossflow. We move to a passive stack style system. This is where you've got your inlets and then going into an atrium. whether it be a full atrium in the building or whether it be just a stack vent duct in the back of the building, back of the room. And obviously then you've got your terminal at the top. That can be either with a roof terminal, or you could have levers on the side of the wall. You obviously cross into it. Again, this is fully natural, so you've got your minimal energy consumption. Again, this gives you a 5 metre effective depth, five times your floor to ceiling effective depth. Then we've got displacement ventilation. So this is where the roof terminal acts as both the inlet and outlet. The way we do this is obviously we have chambers inside the roof terminal, so your wind will drive the air in through the one chamber and down into the room. Obviously that will then force the warmer CO2 laden air up, and on the leeward side the wind will pull it out, as well as you've got your passive effect as well. So this has two systems working on it. So you've got your wind driven doing the pushing and pulling, and also you've got your buoyancy when the wind is not as strong. So we do two ways of doing this. You can do it with a single unit in the roof, or we can duct it to ceiling grills if you want to sort of push it more towards each end of the room. Again, with this system you get 5 times your floor to ceiling height as your effective depth. So then we move on to hybrid systems. Now this is systems where you've got fully natural running most of the time, but in times where there's low wind conditions, or if in the summertime it's warmer, you've got a mechanical to give you a boost. So as you can see, the system's working just standard natural mode, so there's no electricity going on. It's just the windows and your louvers in the walls, and then throw it out. And then obviously we can then, if the wind levels drop or if the heat gains get such that we need to, we can put it in boost mode, where you have a small low power fan inside the roof terminal in this situation. In this situation you've got a small power fan in, which will boost it, and in this situation there's a small power fan in here, obviously boosting the airflow. Then we move on to the hybrid recirculation strategies. So in these situations, the idea being is to retain some of the heat that's generated within the building. So for winter time and cooler conditions, you're not bringing in cold air into the building. So the way they work is you have a chamber inside here, so your warm air will get pulled in, and then part of that outgoing air will get mixed with the incoming cool air to bring in tempered air, obviously with the majority going out still. And then again in here we have a mixing chamber with dampers which will open and close depending on how much mixing we need. So design considerations. So performance of products significantly affects the design of the ventilation system. So 2 important product figures are geometric free area and the CD value. Obviously CD value being the resistance of the product themselves. I'll go back to that. So the interesting thing about this is obviously some products will have the same free area, but we may have different CD values that can dramatically affect the volume of air that can pass through that product. So not all, for example, not all louvers are born from the same cut from the same cloth, I should say. So obviously that can affect it. So bulk airflow calculations. So we use an approved software. So in this we can input the occupancy levels and the requirements in terms of ventilation per occupant, and obviously the dimensions of the room, and this will calculate the requirements for the airflow and the sizing of our products. This is obviously used at design stage to establish product type and size, obviously working with architects and consultants. We can then use these and they can then design them into their building accordingly. And then we move on to thermal modelling. So obviously once we've chosen our products, once we know the sizes, For all our products, we know the key elements to input them into a thermal model. We've worked with VDSL, so we can work with their thermal model to easily create thermal modelling for the building. So another key area is actually the control of the products. Obviously, we need them to respond to the internal and external environment, so we need sensors inside and outside. Obviously, automatic controls enables the airflow to adapt to the CO2 conditions and the temperature conditions, and requires no user interaction. So obviously, they can just run in the background and make sure that the conditions are kept as they should be. BB101, new exert. So the occupant must have the ability to reduce CO2 levels by increasing airflow into the building. So any control system must allow a manual override to allow for occupant's control. There's two areas to this. So obviously with the new BB101, they're pushing more towards full controls, so automated controls for the systems. I think they were finding with the current BB101 it was too easy for the strategy to be openable windows with a traffic light that says you need to open a window, and of course then the teacher or whatever would just go, no, it looks a bit cold outside, I'm not going to bother. They were finding issues with this, so what they want is fully automated controls but with manual override. So say for instance it is getting a bit warm, CO2 levels getting a bit high, the window's open on actuators or the louver's open, but there's some sort of noise happening outside. It also allows the occupant to say, right, okay, I appreciate that, but that is more distracting than the extra warmth in here, so I'll close them up. But of course, after a certain period, they'll move back to automatic just to keep making sure that the environment is correct. Obviously, another key area is speed of reaction. So you're not causing a distraction. You don't want everything opening up really quickly because obviously it's going to make a lot of noise. So you've got to balance the speed of reaction, so the opening time, to make sure it's not too noisy, but it's not too slow that it's, the CO2 levels are going to get too high. And it's also make sure your set point levels are correct in terms of opening points, depending on the environment. And also safety and security, to make sure they close at night. Obviously, with openable windows, if they don't automatically close at night, then potentially you've got a security risk. Another key area is acoustics. So obviously if you've got a natural vent strategy where you've got air passing into a noisy hallway or atrium and you've got a class going on, you don't want all that noise passing in and disturbing your class. So acoustics are a key area to look at. So BB93 obviously is to do with acoustics in schools, so it's obviously to aim to ensure that teachers and pupils can hear each other effectively and to make sure there's no disturbance. Minimum sound reduction point should be 32 decibels between classroom and noisy spaces, and this increases to 37 decibels for SEN classrooms. So I'm going to move on to some of our products, how we do it. So obviously in regards to single-sided and passive stack and crossflow, we would look at actuated louvers. So there's an example of our actuated louvers being installed in a window. So they can go in a wall or a window. Obviously they're controlled by our controls to open and close as required. We have sensors on the outside and inside, so obviously the system will know, right, okay, it's -4 or whatever outside, I need to make sure we don't open these full blast and get everyone with a big chill. So obviously you've got all those elements. I'll go back to that in actual fact. What we do obviously do also with a in front of here we can have a heater coil. So obviously in the winter time it can temper the air if you're not going through a circulation system, obviously to make sure that no cold air is brought in. Roof terminals obviously allow air to pass out through the roof. Obviously they normally include for a controllable louver on the underneath, so again they'll open and close as required. And then again obviously with the what we call the air scoop, which is the allows air in and out. So obviously you've got your chambers inside, so obviously it allows air in and then displaces and allows the air back out, staying air out. There's a side of the round one, and we'll do the square one. And then move on to our acoustic transfer unit, which is what we call the sound scoop. So obviously this allows air to pass through the rooms into the noisy spaces, but reduces, and predominantly it reduces the noise of speech and footfall. I've got a sample of the unit here, what we call the sound scoop. As you can see, it's fairly simple. We've got ABS plastic with these ribs, and then inside we've got some acoustic wool. And essentially, the way it works, the air, sound waves come in, bounce off the ribs into the wool, and they're absorbed by this acoustic wool. They're designed to be positioned up high, and they're designed to reduce the noise of footfall and speech. They were developed with an acoustic engineer, and as you can see, it's a big hole, so they're very easy for allowing air to pass in and out. We do several sizes. That's the smaller size. We do a 600 wide, and we vary in length from 300 to 1200. The highest we can get is 42 decibel reduction through one of those units. Obviously they vary depending on which sizes you use and which lengths. But the 300 square by 1200 will do a 42 decibel reduction. So it's a very, as you can see, it's very lightweight, very easy to install. Obviously we supply with grills either side, so you've got your room side and your hall side, and obviously in this sample we've got a bulkhead which you'll have to build in. They can be fitted above, if you've got a ceiling void, they can be fitted above the ceiling void, obviously with a egg crate grill in the ceiling to allow the air to pass up through and down again. So design assistants, obviously Passivent are the experts, we're here to help. So if you need any assistance in designing, and then that's what we're here to do. Obviously we'll take design responsibility for our designs and demo models. Any questions?
How many attenuators like the one that you showed us would be required for a typical classroom?
So the typical, so this is a 320, we do a 320 by 620, yeah. Typical 32 occupancy classroom would be 2 of those next to each other with the grills on. Or obviously you can have one at one end, one at the other end. Yeah, 2. The effective area here, I think, is 220 square, so on 600, 620, 220 by 500. Obviously with that, because you've got such little resistance there, it allows us to do fairly small units. And normally it's 900, I think, yeah, so when you have the 620 by 320, 900 long, 2 of those will give you the decibel reduction requirements, and also obviously the airflow across. Yep.
Can you just go back to the hybrid bed slide?
Yep.
Just interested to know about that external blueprint, how that works. Yeah, so you've got fresh air in and the exhaust air out.
Yep.
Through the same louver.
Yes. So you've got, with the same louver, you've got, I'm trying to remember how it's designed. The louver is segmented in a way such that the hot warm air goes and is forced upwards, and the cold air is drawn in from below.
So it's not side-by-side figures?
No.
It's top and bottom figures?
So in terms of our product, the current one, that's how it works. We've got one in development at the moment which is coming out we're being told by the end of this year. How that one does it, I don't know exactly. We haven't seen the designs yet, but it's being developed. It's currently in testing to make sure obviously it works before we put it to market. But how that one does it, I don't know exactly because I haven't seen it yet.
But is there a fan in that box?
Yes.
Just
So
one?
yeah, there's a fan unit in this one. In the one we have currently, it's a low power sweep fan, which is mounted under here basically.
In the supply airstream?
Yes.
So you use buoyancy for the exhaust?
Yes. Yes. So the exhaust, you've got the sweep fan. Hold on. Go with me. So, no one's going to be able to see it here. So this is the one we have currently. So in here you've got your low power sweep fan. So it uses the obviously positive pressure to draw air in here and the negative pressure to allow that air to go out. There is a damper in here which opens and closes as and when required, so obviously if you don't want to bring in any of the existing air through it, then that will close to just allow the one to go out to the other basically. But yeah, it would use the buoyancy to allow in natural mode it will use obviously the buoyancy to so your wind forces will drive the air in, and obviously buoyancy will then force your air out.
If I saw that detail right, is there a louver, then a plenum, then your unit?
Yes.
So what's to stop air from recirculating in that plenum between your unit and the louver?
There's a
Is there a divide, a baffle in?
there is a baffle of some sort. I have to be honest, this unit here, I've not actually seen one in person.
Okay.
I've been in person for 4 months, so, and I know the reason we're developing a new one is because this one was deemed to be not, as good a performance as it should be. So we try not to push this one, to be honest.
That unit on
We
the
talk
top,
about obviously the system, but because obviously it is a system that's available.
turret unit,
Yeah.
has that just got one fan in it as well?
Yes. So the turret unit. I'll go and get another one. Show you the whole pack. So inside the turret itself, in here, there's a mixing chamber, which will adjust up and down depending on how much you want to recirculate. Let's get the unit up here. So if you see here, so we've got a sweep fan in here. You've got a mixing chamber with slots in here. So depending on, if I move over to here, you see. So depending, obviously, in boost, this is in just natural mode. That sits up to it, allows all the air just to pass out. In boost mode, that comes down, and obviously the sweep fan will come on and then force all the air out through the fan. And then in mixing mode, the fan obviously goes in the opposite direction, drawing air in through the top chamber, and then air will get pulled through, obviously through buoyancy through there, and then depending on how much you want to mix, that will move further up or further down, opening up that aperture as much as it needs to. So obviously it will just rely on sucking through that amount of air, if you see what I mean. And then obviously, again in recirculation mode here, you've got, if you close it completely, then you've just got it boosting, so that's with the fan on, boosting air coming in. So this is for summertime, you can boost the air coming in with air going out as well. But so the idea being that all that happens inside of this chamber. So obviously on your ceiling detail, you've just got just a flat louver like you'd have in a normal roof terminal. So there's no boxes dangling down doing all the governance. Obviously with that, I'll just say it only works for single story, or obviously if it's a two-story, the top story. It's not, you can't duct down, if you see what I mean, with that system. Any other questions? Yep.
One more to know everyone.
Okay.
Is a hybrid system,
Yeah.
is the CO2 footprint of the building less than if it's just natural rearranged?
Not necessarily. The idea of a hybrid is obviously in the summertime. There's two forms of hybrid. So you've got the hybrid, which is like a hybrid boost to the natural, where you've just got a fan, which is either helping, obviously, if the wind conditions are low, then it will obviously help draw air out, obviously by turning on to create that movement of air. And then you've got your recirculation hybrid. They're both classed as hybrid, but with the recirculation system, the idea being that in the cold winter times you don't have to worry about putting additional heating into the system. So obviously with a standard natural system, if you've got air cools in a wall and they're low down, for instance, then you don't want cold drafts. You might have to put heating elements in it, which obviously then requires power, heating to it, which creates CO2. So I think from most of the studies they've done, there's not a lot of difference because of that factor. If you didn't have the heating elements and you just had the cold air and the thing, and with the recirc, then because you're using power to do it, then technically your CO2 is slightly more, but it's minimal. I mean, the sweep fans themselves in our unit, I think they're rated at about 40 watts, the idea being is that they're only really on, you know, a few weeks or, you know, whatever days they're required. So school's obviously off during peak summertime, so you haven't got to worry so much about peak summertime temperatures, but obviously they're still there in June. And obviously, as long as you've got good wind, then you're going to get a good flow. But if you have got that drop in wind, then you just got that there to help. But I couldn't tell you definite. It's you know 10% more or 5% more. But from what I know, it's not a big difference.
Okay. I mean, the only reason I asked is because we just done a school and we was questioning, this line in the EFA spec about cold drafts, and most of the building stuff in the UK is like 1950s old radiators, and they can just about manage to maintain what they've got. So they've got all these new buildings going up with extra systems and components that have got to be maintained.
Yeah, I mean, obviously the idea with fully natural is the maintenance shouldn't be a great deal, because all you've got, the only moving part you've got is an actuator. Everything else is technically sits there solid. You know, your louvers and your crossflow, like for instance the sound scoop. There's no moving parts, so the only thing you've got to do is clean them. So the idea of natural is that obviously with your air conditioning, you've got your compressors, you've got your condensers, you've got your units with all your fans and everything like that. There's a lot of moving parts in there that have got to be maintained and or replaced when they break down. Whereas with a natural system, the idea is that there's not a lot there to break down, therefore the maintenance should be a lot less.
The school does work, so there's a bit of a conflict where the school didn't want the whole system because there's a school that required the EFA to allow it.
Yeah. Well, there is that. I mean, to be honest, I've heard of. So I went into an architect's in Cambridge, and they'd just done a school with the hybrid system, and the I can't remember who it was, but he was like the governor of the area. He had like this formal schools, and he told them quite bluntly, "I do not want one of those hybrid units." And again, he says it looks like a fridge on my ceiling, and it makes a great racket that all my teachers are complaining about. So. Obviously, I don't know what unit. She wouldn't tell me what unit they used. There's several on the market. The one we're developing, we're hoping we're doing it really, so it will be really quiet. Because I know that is one of the complaints of them, of the hybrid units, is the noise. Because obviously teachers, they click in and out. You see, obviously as the CO2 levels rise and temperature rise, they'll click in to give them that boost, and then as it drops, they'll click out and stop. So they start hearing it. If you see what I mean. So obviously we'll try and design them to not be like that. But Yeah, like you say, it's one of those things that some people like them, some people don't. Some school authorities like them, some school authorities don't. Some school authorities can afford them, some school authorities can't. There are systems where you do a hybrid mix between natural and air conditioning, but they can be very expensive. We did one, Passivent did one about 8 years ago, and our MD went down there for some reason. I can't remember. Oh, he went to see the consultant who did it, and that school absolutely loves it. It's a brilliant system. You know, it works really well. The conditions in the building are really, really good. You know, but it was very expensive. So, any more questions? I hope I answered the question there.
Do you have any problem with particulars in the air or dust and everything coming into the building?
Yeah, so obviously we have meshes on our back of our louvers, so you don't get any airborne insects or like that. But in terms of dust filtration, obviously with natural you've not got a lot of pressure to play with, so if you start trying to put filter media in there, pretty much stops the system working. Again, that's where you've got to look at the application. You know, if you've got an area that you know is particularly dusty, I don't know if there's a quarry nearby or something like that, then maybe you've got to look further to the hybrid or mechanical solutions. Just as if you've got an inner city school, you know, near busy traffic areas, then potentially you've got to look at mechanical systems because you've got pollutants. You know, it's all well and good bringing the CO2 out, but if you're just bringing in nitrogen oxide and more carbon monoxide from fuel emissions, car emissions, then you know it's just as, probably worse. So obviously that's where you've got to look at the key areas. I couldn't say that from my experience, my short experience, that dust has been a big issue that I've heard about. Not had it mentioned to me at all. But yeah, everything's covered in dust in the morning, sort of thing. I guess with the louvers the way they are, any airborne would, you know, you'd hope would sort of get sort of thrown out the airstream a little bit because the air's got to move. The air path sort of moves around a bit. I know with these, we advise that they clean. Obviously, it's got this sort of quilt material on it, which can collect the dust and can affect the performance. So in our O&M manual, it sort of recommends that these are cleaned on a, I can't remember if it's a monthly or a bi-monthly basis. You know, they just take the grill off and just give it a wipe to get rid of any dust, so it can affect the acoustic performance.
Well, thank you very much, Stuart,
You're very
for
welcome.
today's presentation. There are a very nice selection of the different methods of the natural ventilation in buildings, in particular in schools. Our next subject is on the 4th of October on evacuation lifts. And let's all thank Stuart in the usual way.